Okay, welcome to this first lecture in EE381. So this is the first lecture, an introductory lecture. My name is Umut Orguner. I am a professor in Department of Electrical and Electronics Engineering. And the second instructor of this course is Kemal Leblebicioğlu. I think you will meet him in the second half of the semester. So here is my contact info. The best way to reach me, of course, also in the pandemic, is via email. And you see my phone number and the office. My office is, if you happen to want to visit me, is in E block of Department of Electrical and Electronics Engineering. So it is the building in front of the Industrial Engineering Department. And there is a writing there that is Optimus Prime. So there's this large door, and on the other side of that building there is the entrance. So I'm sorry for my setup here. It looks a little bit slanted here, but this is the best that I can achieve for now. So now let us go over this presentation. In my lectures, I will use the board mostly, and this is the only lecture actually that I'm going to use slides. So let us go over the presentation. So I have the course aim, I will mention about this one, and we have the control examples. And before that, I'm actually going to be talking about what control is. So, and then I have the control principles, and we're going to see one fundamental principle that we're going to be investigating, and that is going to be the principle of feedback. And then I will talk about what we will learn during the semester, and I will give a tentative course content. So this is going to be the course content that you see in our syllabus. I will go over item by item, and then I will try to explain each one and their relationship with the course. So automatic control is just one of the main fields of research in many engineering departments. Of course, you are taking this course from Electrical and Electronic Engineering department, but there are control courses in mechanical engineering, aerospace engineering, even chemical engineering, and there is a recent addition to this list, which is the computer engineering department. So you see that almost all engineering departments are actually taking this type of course in their undergraduate study. And the first thing that I need to explain here is what control is. In order to be able to talk about control, I have to first talk about what a system is. A system in electrical engineering language, or I don't know, in a system theoretical language, means something that we can model using mathematical equations. So it can be anything that you can model with mathematical equations. For example, it can be a physical system, a mechanical system. It can be a hydraulic system, something related with the fluids. And it can be an economical system, it can be a social system. As long as you can mathematically model it, we are going to be calling such entities as systems. And these systems are going to have some inputs and they're going to have some outputs. In general, control is related to the output of the system, and actually it is trying to select the input of a system such that the output behaves in a way that we like. For example, if I have an economical system, if I have some inputs of the system that I can adjust, then if I have some outputs that I would like to change, then control of that economical system means to choose the inputs of the system that we can change to actually make the output of the system behave in a way we like. And here I have the more rigorous definition. Control is interested in making systems behave as we like. So I define what a system is, and by making the system outputs behave as we like, and while doing that we are using the measurements of the system. So control is choosing the inputs of the system such that the outputs behave in a way we like. And how do we achieve control? We achieve control by actually looking at the measurements of the system. And this is actually called feedback, which is the main principle of control that we are going to see in this course. And the aim of this course, after defining what control is to provide an introduction to the basic principles and tools for the design and analysis of feedback systems. So we're going to be talking about some systems, and then we're going to apply feedback to them. We are going to call the resulting systems closed-loop systems, and we're going to be analyzing their performance, and we are analyzing how we can design such systems in order to be able to satisfy some design criteria. So this was the course aim, and then I will talk about where is control necessary. So most probably you have already encountered a control application. Even in cell phones there are control applications. And actually, you don't know about control when everything works here. So that is something interesting. If there is control, then most of the time you won't notice it because everything is going to work perfectly. But it is often hidden in applications, so you won't realize it directly. And many technology companies try to apply control. We have many interesting applications, and one of the basic properties of control theory is that it's a very, very mathematical theory. So you have to like mathematics in order to be able to like control. So it is more mathematics than physics, actually. In some electrical engineering courses, we have more physics. For example, in electromagnetic courses, we have more physics than probably mathematics. It is my opinion, at least. But in this course, we are going to have much more mathematics than physics. So let us look at some control examples. In the cars, modern cars, you see lots of these abbreviations. Actually, each one of them is actually a control example. So this ABS, an anti-lock braking system, or electronic stability control, they are inherently control applications, and they are working while you drive your car. The second example that I can give is the industrial robots. So these are doing the same motion over and over in a factory, taking something, and then they're taking it somewhere else, and they're doing some job here. And they have to do the same thing over and over. And for them to be able to successful, you need to control these electric motors that are placed in the joints of this industrial robots. And one problem about this is that these are usually flexible. And people try to want them actually lighter and lighter, so they don't want heavy robots. And when they become lighter, then they become more and more flexible. And that actually places a restriction on the properties of such robots. You have to control them in a very, very good way to actually avoid the oscillations that are caused by this additional flexibility in these robots. So this is also a classical control example. The third one is the mobile robotics. So they're entering our lives more and more. So you might probably have seen this Boston Dynamics robot here. It is like a, I don't know, maybe donkey. And we have a robot here that is in our department, which is designed for very, very rough conditions. It is called a 6-leg robot. Of course, you have to control every electric motor that are put on these joints here, and also additionally you have to put some more control stuff into these robots for them to be able to work safely. The fighter aircrafts are another example. When you actually get in a commercial airplane, when you fly with a commercial airplane, those airplanes are actually designed in a stable way. What does that mean? That means that when the engines are shut off, when you stop the engines of the airplane, then those commercial airplanes would actually only glide. Okay, so you won't immediately fall down to the ground, but they will actually glide. So they have a stable structure. But the fighter airplanes have to make lots of maneuvers quite fast. Therefore, their structures are usually designed in an unstable way. And without actually using control theory, it is impossible to fly these devices here, these vehicles. So if the control is not sufficient, then obviously these type of airplanes would fail. So I will give some examples from the health here. So in diabetes is şeker hastalığı in Turkish, and in diabetes, people's bodies cannot control the glucose levels in their blood, and in general, the organ that is controlling the glucose level in the blood is called the pancreas. And if the pancreas goes out of order in a body, then you have the diabetes disease. So here, what we can do here is to put a mechanical device into the body of the person, such that the glucose levels would be measured from their blood, and then we can actually inject glucose into the body intravenously. So we see here that an application that is a health application actually, and that is using a controller. By measuring the glucose level in the blood, it is trying to control the glucose level in the blood. We're going to see the connections between these applications. So another example might be the economical example. So I don't know if you would be interested in economy. At least I know that you take multiple courses from the economy department. So here, one system, an economical system that we can talk of is the system between the interest rates and the inflation. So as you increase the inflation, as you increase the interest rate, the inflation would be decreased, and we have a relationship vice versa. So here, if we think the economy as a system with the input, which is the interest rate, which we can actually adjust by using the central bank here. That is what central banks do. They adjust the interest rate in the country, and the output of that economical system can be the inflation. Okay? So we see here that we can actually try to control the inflation in a country by adjusting the interest rate. And that is actually what central banks are always doing. So now let us try to go into some abstract domain here. So when I say a system, in general that system has an input, it has an output, and some other inputs that are shown here by W. This input U that we call is the control input. And control input is the inputs that we can control ourselves from the outside. The second input of the system is called the disturbance, that is W of T. And the thing that I would like to control is shown by Y of T. It is the output of the system. And in control, we are trying to actually change the input or select the inputs of the system such that the output behaves in a desired way. Okay? And how do I quantify that desired adjective here? We usually quantify it, or we usually model it with another signal that is called R of T. This is called the reference signal, and what we want from control is this Y of T, the output of the system, to actually follow this reference signal. R of t. So the reference signal is the ideal thing that we would like the output to do. Okay? And does that do that? How does it do that? It does it, or we do it, by choosing the input in a satisfactory way. That is what control means. And here there are disturbances, and these are actually working against our control objective. Okay? So disturbances, as the name implies here, they are the inputs that we cannot control in the system. So they are actually, most of the times, they are working against our control objectives. So then what is control? Control is choosing the input U such that the output behaves, output is close to the reference against the disturbances. Okay? So this is the abstract definition of control. So here let us go over this text here. The thing that we would like to control is the system, input, output, and the disturbances. The aim here is to design the control input. I want to choose this thing so that the system, the output, behaves as wanted, which is it becomes close to this reference signal despite the disturbances. So we are going to see examples of this I have given already some examples, and in those examples we are going to try to understand which signal, which variable corresponds to which variable here. So here this U of t, Y of t, R of t, and W of t, they are all functions of time, and they are called signals. So we call a function of time as a signal in this course. So now let us look at some examples of such signals. So here I have 4 examples, and I will go over them one by one. So the first example is the control of the speed of a car. So the car speed control, and it is usually called, in technical terms, it's called cruise control. You might have heard it if you try to actually look at some car advertisements. So here cruise control is the control of the car's speed. So we want the speed of the car to behave in a way that we like, and we are going to use the inputs in order to be able to achieve that aim. So here our system is the car body here, and the output of that system, the thing that we would like to control, is the speed of the car. Okay? So that is the output signal, Y of t. And how do we control the speed of the car? Actually, there are automatic systems that achieves that, and this is done by adjusting the throttle and the brakes. Throttle is gaza basmak. Throttle is that thing, and which increases the speed of the car, and brakes are fren. That is actually decreasing the speed of the car. And in recent cars, there's always a circuit that actually tries to adjust the speed of the car if the user gives an order to do so. So here so for example, you can adjust the knob in your car so that the speed remains constant at 90 kilometers per hour. That is a cruise control objective. So we want the speed of the car to be equal to the desired speed, that is 90 kilometers per hour. Okay? And our reference signal is therefore a constant here. It is a constant at 90 kilometers per hour, and we want the speed of the car to be equal to that constant. So, and in order to be able to achieve that aim, we are going to use the inputs, throttles, and the brake. So what can be some what can be some disturbance signals in that case? So in that case, of course, the car might be going on a slope so that it might slow down if I don't do anything. That is one of the disturbance signals that we can achieve, the slope of the road that the car is traveling on. Or the air resistance. As the car goes faster and faster, it's going to encounter more air resistance. That is called drag, actually. And it is also a disturbance that is working against our control objectives. So this is our first example. The second example is, so we've seen some examples of these signals here. The second example is the room temperature. So suppose that I'm trying to adjust or I'm trying to control the temperature of this room. Okay? So suppose that it is at 23 degrees, it's a little bit cold, and suppose that I would like to bring it to a constant level, 27 degrees, okay? In that case, what can be these variables? Our system is this room, or the air in this room, and the input that we can use here in order to be achieved that is the air conditioner, okay? It can actually cool the room or it can heat the room in order to achieve our control aim. The output of the system is the temperature of the room. So we are trying to control the output of the system, which is the temperature of the room. And the reference is the desired temperature. It is again a constant. I really do not want the temperature of the room to behave like this, in an oscillatory way. I want it to be a constant for the comfort, okay? And what can be some disturbances? In this case, there are heat loss from the windows. So if it is winter, then it is going to be more difficult to heat this room. So the outside temperature, or here I can say heat loss from the windows, is actually a disturbance in our control system in this case. So here I have already given these last two examples here. It is the glucose metabolism in the body. It is the diabetes example. Here we are trying to control the glucose level in the blood. This is the output. And the insulin is the hormone that we give from outside because the pancreas is not working. Insulin is our control input. And we have a desired glucose level in a patient depending on their weight, and therefore we have some constant reference signal here. We want the glucose level equal to a constant. And here what can be some disturbances? So during the day we are trying to keep the glucose level in the blood at a constant value, and but the patient is going to eat and drink some things that contains glucose, and that is going to increase actually the glucose level in the blood. And that is actually against our control objectives. So we are trying to control the glucose level despite the glucose intake of the patient here. And the last example is the economy example. And here we are trying to control the inflation in the country. Usually we have the inflation goal here, which is the 5% inflation per year. And the central bank is actually using the interest rate to control the inflation. And what can be some disturbances in this case? Of course, the economy is a very, very complex system, and there are really lots of disturbances in that huge system. But some very obvious disturbances can be politics or elections in the country, for example. So they're going to give a disturbance to the inflation. Or there might be a recession in the country, which is going to be a problem for the central bank, and it's going to make the control of the inflation more difficult. So now let us go into the feedback idea. So let us go back to the control example, controlling the temperature of this room here. So the room the room has a temperature. So suppose that I don't know that temperature, and suppose that I want to bring the room to a constant temperature, 27 degrees, okay? In order to be able to achieve the control here, you have to measure the current temperature of the room, okay? Without measuring the current temperature, you won't know whether to heat the room or cool the room, okay? So this measuring idea, measuring the current variable values in order to be able to design the input is called feedback. When you measure the current temperature, you know the desired temperature, and then you can compare those, and then you can decide actually whether to heat or to cool the room. That is the idea of feedback. Without feedback, you really cannot achieve a good control most of the times. So this is the measuring the current temperature. It is called the feedback. Suppose that it is 23 degrees, then you know that you need to heat the room to reach the desired temperature here, which is the 27 degrees. Usually we show this idea like this. This is the system that I have shown before. It has some control inputs that we can change, and it has some outputs that we would like to we would like to make them behave as we wish, and it has some disturbances here. What we do here is that we take the reference signal and we take the current output of the system and we put them into another system, and this system has the job of giving the input to the actual system. This additional system that I use here is called a controller. And if usually the controller is a human being. If I'm in control of an air conditioner in this room, then I know whether to heat or the cool the room. Okay? So in that case, that I am the controller. Okay? But if you would like to achieve this job automatically, then I have to put here an artificial system which is called just a controller, and this controller has to look at the reference signal, and it has to look at the current output value, and it has to decide what input it should give to the actual system. It has to decide whether to heat or to cool the room automatically. Okay? And this part of the system is called the feedback loop. All right? So this part is called the forward part. This part is called the feedback part. And in the overall, I have a feedback loop. Without the feedback loop, this system is called an open loop system. Loop is not closed. And with the feedback loop, we call this system a closed loop system, and we would like to investigate what the properties of such a system would be. That is going to be one of the main aims of this course. We are going to have an open loop system, and then we are going to close the loop to obtain an automatic feedback system. And we are going to try to understand the properties of the closed loop system, and in order to change those properties, we are going to put here some controller systems, and these controller systems are going to be some artificial systems whose parameters we are going to adjust to satisfy some performance requirement from this control system, from this closed loop system. Okay? So here, this system, I cannot change what is inside this thing. Okay, this is the system itself. This is the room itself. I cannot change what happens here. Okay, but here this is an artificial system. I can change my air conditioner. This is an artificial system that we put into the picture here, and by adjusting the properties of this artificial system, we are going to try to adjust the properties of the overall closed loop system. That is that is called the controller design, and it is called the performance-based controller design. So in the case of cruise control here, I have the following picture. So I have the car itself. I cannot change the car. It is given to me, and I would like to change its speed, make its speed behave in a way I like, and I will do that by applying throttle or the brakes into the car. So this is the knob that the driver is actually adjusting. He or she gives the reference speed here. So there is, if your car has a cruise control, then you have a knob somewhere in the car that you can adjust the desired speed. This is the reference signal. And there is a circuit in the car that can automatically apply throttle or brakes in order to achieve a desired speed. Of course, that circuit has to know both the desired speed, so this is the reference signal, and it has to know the actual speed of the car in order to decide whether it has to apply throttle or the brakes. So in that case, that circuit is called the controller in this application. And in the economy example, we have the economic system, millions of variables. So each person is a variable in an economy. So we have the central bank can control the interest rate, and the output of the system, the thing that we would like to change is the inflation rate in the country, and we have to know the current inflation rate, and we also have the desired inflation rate here. Here I put 5% here, which is a fine inflation rate, I think. And then by knowing the desired inflation rate and the actual inflation rate, the central bank officers decide on the interest rate to apply in the country. Okay? So in that case, I have again a feedback loop, and we would like to be investigating what properties we have, or what type of officers should we put into the central bank. Okay? Which officer can adjust this in a nice way, and which can't. So now let us look at what we will learn in this course. In this course, we are going to ask and answer the following questions. Well, the first question is, how do we describe the system to be controlled? So when we get a system, as I told you, you need to be able to model that system using mathematical equations. That is called mathematical modeling. And when we get a system to control, the first thing that we do is to pass it into the mathematical domain. So we have an actual system. I have this room to control the temperature, but in order to be able to do something about this control, I have to write the mathematical equations relating the temperature of the room to the input variables. So I have to be able to use mathematical modeling. That is what we are first going to do in this course. We learn how to mathematically model very simple systems. These systems are going to be, for example, electric circuits. They can be mechanical systems, or there will also be some input types that is called the DC motor. But we are going to see them one by one. The second thing that we are going to do is that we are going to define some performance measures for the control systems to satisfy. What can be those performance measures? So suppose that I go back to the cruise control example. Suppose that currently the car that I drive is going with 70 kilometers per hour speed, okay? And suppose that I want the cruise control system to bring the speed of the car up to 90 kilometers per hour, okay? I want to go faster, all right? So would you really be happy if the automatic cruise control system would bring the speed of the car to the desired speed, 90 kilometers per hour, in 2 hours? So you really probably wouldn't like such a thing. Okay? So you want this to be fast. So you want the speed of the car to come to the desired speed in a few seconds or I don't know, half a minute or something like that. Okay? Do you really, for example, suppose that I have the same situation, would you want the speed of the car to come to the desired speed, 90 kilometers per hour, in 0.1 milliseconds? So the speed of the car going from 70 kilometers per hour to 90 kilometers per hour in 0.1 milliseconds. So if you think about the speed-acceleration relationship, you know that if the velocity changes from 70 to 90 in a very, very short time, the driver and the passengers are going to encounter some acceleration forces. If you do this in this very, very fast manner, then it's not going to be good either. So you really do not want the cruise controller to be too fast. You don't want it to be too fast, because in that case, the accelerations that the passengers are going to encounter will not really be comfortable. And you don't want it to be too slow. So you really do not want to wait for 2 hours for the speed of the car to come to the desired speed. So that means that there should be a performance requirement on the controller that we design as a cruise controller. Okay? There have to be some performance, and this performance requirement is going to tell us that the speed of the car should come from here to here in a specified amount of time. That is a performance requirement on the control system. And while designing this control system, while designing the controller that we put into that system, we need to take care of that performance requirement. And there are some standard ways in control theory to actually specify these performance requirements. We are going to see those performance requirements. And then we're going to see how do we analyze the system to be controlled. So we're going to see what is the open loop system, it is the car itself, and what is the closed loop system. What happens when I close the feedback loop? And then we're going to see how we design a controller. So what type of system I should put instead of that controller block. So we will see that there are some standard types, and we're going to see how to design those in order to be able to satisfy the performance requirements. And finally, we are going to see how do we analyze the feedback system, the closed loop system, and what can go wrong. So sometimes, as a feedback system, a system with feedback can be much, much worse than a system, the same system without a feedback. And we call this thing related to the performance of the feedback system as a stability of the feedback system. So sometimes if you design your feedback system in a really bad way, then your system is going to be much, much worse than what you started with. Okay? We're going to see what the problem is, and this problem is going to be, again, something called positive feedback, and it is going to be related to the concept of stability. So now let us look at the tentative course outline here. So we are here at the introduction. So in this course, we are going to use some mathematical models, and these mathematical models are going to start with differential equations. So differential equations will be only the start. We are going to see that handling differential equations by themselves is really difficult. So we're going to instead go into something called Laplace domain. You have probably seen Laplace transform in your differential equation course, but here, at the beginning of this course, I would first like to review this Laplace transform that we are going to use to transform differential equations into new types of models in Laplace domain. And then we are going to see the concept of mathematical modeling. And in terms of systems, the mathematical modeling that we're going to apply on the electric circuits, mechanical systems, and something called the DC motor. So since you are not really electrical engineers, you have to think about these only in terms of mathematical models. You really do not have to understand every detail here, but you need to be patient here. So once we present the mathematical models here, they are not really going to be something difficult that you cannot apply yourself. So if you be patient in this part of the course, then I'm sure all of you are going to be able to write the mathematical models for such systems quite easily. And it's going to be useful at in the other parts of the course. Then we are going to see system representations and block diagrams. So we are going to see there are different types of mathematical models that we can come up with for a single system. For a mechanical system, I can write differential equation. Another type of model we are going to see, it is transfer function. It is a Laplace domain differential equation, I can say. And the last type of mathematical model that we will see is called a state space representation. So in total, we're going to see 3 different system representations. These are 3 different mathematical models that we can obtain for a single system. Of course, they are in some way related to each other for a single system. We're going to see the relationship between those. And usually we're going to be working with block diagrams. Connected systems. The output of one system is connected to the input of another system. And we are going to, also we will have some feedback loops. These are going to be in the block diagrams that we are going to use. So this second part of the course is called time domain analysis. And this is nothing but the performance, specifying the performance requirements of a control system. So in this part that is called time domain analysis, we are going to learn how to specify the performance requirements from a system, okay, from a control system. And the third part is related to this important concept of stability. As I told you, sometimes feedback makes a system worse. And we are going to learn when does that do that, okay? So here, that is the concept of stability. And this last part of the course is the state equations. So we're going to see one of these modeling types that is called state space representations, and we're going to apply the earlier ideas to the state equations or state space representations. So this is actually all that I can give about these slides. So I would like to finish this lecture by working on a very, very simple example. For that, I'm going to turn off the projector here. So let us start with something that resembles what we are going to do in this course. So I will first, so this is just introductory. So really, I'm going to work on some things here, some pieces of some information that we're going to give in the course. You really do not have to understand all of them, or you really do not have to understand any of them, because we are going to be repeating these over and over when we go to the lectures in detail. But in this introductory lecture, I'm just going to go over some pieces of information, some pieces of concepts that we are going to see in the course, and I will try to explain what each part means. So here, let us look at the cruise control example. So as I told you, cruise control is the control of the speed of a car, okay? And in order to be able to apply the control ideas into cruise control, then I have to have a mathematical model of a car, okay? So what can be the mathematical model in this case? It is going to be looking like something like this in this course. It is going to be a mass that is shown with this block, and it's going to be having a friction that is represented by the friction coefficient B. Okay? So the car has a mass M, and it has some friction with the ground that is shown as B. And here a force is applied onto the car, which I show as F. And the car has a position that is shown by, let us say, Y. Okay? So in this case, the position of the car is Y, and I would like to control its speed. If the position is Y, then what is the velocity? It is going to be actually Y dot, okay? It is going to be the velocity that I would like to control. So this is Y dot, which is equal to V here, which is my output, all right? So here, this is a system. I have a mathematical model here. It has the input F, this force that we are able to control by applying throttle or the brakes. We apply a force onto the car body, and I have the output V, which is equal to Y dot. Okay? Then the cruise control is nothing but selecting the force F to be applied onto the car to make the speed V equal to a constant. Okay? So I have a reference speed, of course, and that is shown by R of t. This is usually going to be a constant, just R0. Let us say that it is 90 kilometers per hour. Okay? That is the reference speed. All right? Now I'm going to be obtaining a mathematical model for this system, and it is going to be a very, very simple physical model here. All right? So here, you are not going to understand this part if you did not work on classical mechanics or any other advanced physics. You won't understand this at once, okay? But you're going to understand when we start to work on these topics in more detail. So I will start with the Newton's law. So that is going to be m times y double dot. This is the m times the acceleration. The right-hand side is going to be the net force applied onto this mass. Okay? And here, one of the components of the force that I apply onto the right-hand side is going to be F. That is applied by ourselves here from the outside. And the second one is going to be the friction force. And in this course, we're going to obtain the friction force with an equation, something like this. Okay? B times y dot, B times the velocity. So as the velocity of the car increases, the friction is increasing. These N and B are positive constants here. So as I told you, if you didn't understand what I did here, it really doesn't matter. When we start to work on these topics, I'm going to go over everything in much more detail. So here, you see that I have y here. This f is the input of the system, but y is not the output. What is the output? It is y dot. Okay? So I will write everything here, everything instead of this f here, in terms of y dot. So I'm going to write something like this. M times y double dot is nothing but y dot dot. And that is f minus by dot. Okay? And we see that y dot is v. It is the output variable. M times v dot. This is v. I still have a dot here, so this is going to be v dot. Is equal to f minus b. Y dot is b. Okay? So this is an example of a mathematical model for a system that we would like to be working on. All right? It contains only the variables of input and the output here. This is called the differential equation representation of the cruise control system, the car system. It is a differential equation representation. So I can write the system with something like this: mv dot plus bv is equal to f. On the right hand side, I only have the input f, and on the left hand side I have the output variables. So here, that is a mathematical model. In general, we don't want to use this differential equation model. Instead, we are going to be using something called a transfer function. And it's a Laplace domain mathematical model. And here, I'm going to write the transfer function of this system. We will usually show the transfer function of a system with g of s. It is a function of a complex variable, which is equal to s. And g of s, the transfer function for this system, I'm not going to write here how I obtain this, but I will just write the result. You will know what such a thing would mean. But this is going to be the mathematical model that we are going to be using in order to represent this cruise control system. All right? This is called a transfer function mathematical model. And if I show the cruise control system, sorry, I will erase this part a little bit. Then I'm going to have this g of s, 1 over ms plus b. I have my input, which is f here, and I have my output here, which is the speed that I would like to control. Okay? So what was the feedback idea? Feedback idea is going to be something like this. I have the reference speed here. This is R0, which is equal to 90 kilometers per hour. And I will here put a subtractor. Okay? And I will feed the actual speed of the car back to the input side of the system. That is going to be called the feedback. All right? And here I have this difference. The reference minus the actual speed. Okay? So if the actual speed is smaller than 90 kilometers per hour, then this difference is going to be positive. If the actual speed is larger than 90 kilometers per hour, this difference is going to be negative. Okay? And then here we are going to put a block. This block is going to be just a controller. Okay? What type of block should this be? So the first thing that comes to mind is that why just not put here a single multiplicative constant k? So this idea is actually quite valid. Suppose that k is positive, okay? And in the case that I put a single multiplicative constant k here, then this block is called a proportional controller. And then the task is to select this constant k such that the overall control system, the closed loop system, satisfies some performance requirements. So sometimes if we choose this k very, very large, then some bad things can happen in the cruise control system. If I choose my k large, then these forces that I apply into the car are going to be very, very large. So I really do not want such thing. I want the comfort of the passengers. So really, I really do not want a very, very large K here. Similarly, I really do not want a small, very, very small K. All right? In that case, the control can be quite slow. So the speed of the car goes from one point to another point very, very slowly. It's really disturbing if you are the driver. Or the speed of the car tries to go from one point to another point in a very, very fast way. In that case, you're going to hit your head to the seat, and the passengers are going to experience an acceleration which is not really good in terms of comfort. Okay? So here let us look at what this system does here. So if the actual speed of the car is smaller than 90 kilometers per hour, then this difference is going to be positive. Okay? And I'm going to multiply this difference, which is positive, with a positive number. Then that means that I'm going to apply a positive force onto the car, which means that my velocity is going to increase. A positive force means that the velocity is going to increase and it's going to get closer to the 90 kilometers per hour, the desired speed. On the other hand, if the actual velocity is larger than the desired speed here, in that case this difference is going to be negative. And then I'm going to multiply this negative number with a positive constant, which is going to give a negative force. That means that we're going to apply the brakes onto the car, which will make the speed of the car smaller, which is closer to the desired speed here. Okay? So that is how a control system, a feedback control system works. So this is called a negative feedback here. Okay? Because of this subtraction here, this is called a negative feedback system. And by adjusting this K in a nice way to satisfy some performance requirements, then we would obtain an overall cruise control system. So as a final point in this lecture, I'm going to try to explain to you what happens if I choose this K in a wrong way. Suppose that I don't choose K as a positive number. Suppose that I am not really a good control engineer, and suppose that in a wrong way, suppose that I choose this K as a negative number. Then what is going to happen to this feedback system? Let us try to examine that. So let us say that the actual velocity is larger than 90 kilometers per hour. Okay? In that case, this difference is going to be negative. This is larger than 90 kilometers per hour, then this difference is going to be negative. Okay? And I have a negative K, negative controller gain here. A negative number times a negative gain here, it gives you a positive force. Okay? So the car was actually faster than the desired speed, and my controller tells me that I have to apply a positive force onto the car. The car is going to get even faster. Okay? We are getting further away from the desired speed. V was larger than 90 kilometers per hour, and it became even larger now. Then what happens then? This V became larger. This error became more negative here. This is still a negative number, but its magnitude is actually larger than the earlier negative number. So then this is multiplied by negative K. And I apply even a larger positive force to the car, making the car even faster. So this loop continues to work over and over again, making the car faster and faster, getting away from the desired speed. This is called the instability problem in control. And this is caused by the feedback here. Okay? Without the feedback, our car is quite fine. But with the feedback loop, with the wrong feedback loop, we have caused some variables to increase indefinitely. That is called a stability problem, and we're going to see how to detect such problems, or how to analyze such problems, and how to avoid them in this course. So this was some introduction to the ideas of this course, and I hope I could give some glimpse of some ideas and the concepts on this course that we are going to see. In the next lecture, we are going to start with the Laplace transformation. So we're going to start with these S variables, how to obtain those, and I'm going to be talking about why they are useful. It is actually the case that this model is much more useful than this differential equation model, as you're going to see in the next parts of this course. But that is going to be all for this lecture. Thank you for listening.